Hi, I am Professor Shiva Panchakshari. In this video, I am going to explain about the Stoke's theorem. The Stoke's theorem is basically a theorem which relates a line integral to surface integral. And vice versa. This is a very well-known theorem in many of the applications to convert line integral to surface integral. There is another theorem which is doing similar job, that is divergence theorem, which relates a closed surface integral with the volume integral. But Stoke's theorem relates a closed line integral with a surface integral. In this case, the surface S is the surface enclosed by the path C. So to understand this theorem better, let us choose a closed path of any shape. We shall assume that the closed path is taken in this direction, counterclockwise direction. So let us look into the left-hand side of the theorem. That is, line integral of this magnetic field over the closed path. The closed path, this particular closed path has four different sides. So let us take any one of them. So we have to evaluate H completely on this closed path. But there is a dot product here. So the dot product expands H dot dl as H dl cos theta, where theta is the angle between H and dl, the field and the path. So any vector H, this theorem is applicable to any arbitrary vector. So any vector H which is oriented in an arbitrary direction can be splitted into two components. So we know that. So the vector is divided here, are identified as two components which are perpendicular to each other. So any one of these components, let us say H1 and H2, any one of these components which are parallel to the path. So let us say this is the path chosen. And on this path, I'm going to choose a differential length dl, which is oriented in this direction. That is the direction of the path itself. Then this path dl is parallel with h1. So I can call this h1 as ht, tangential component or parallel component with dl, whereas h2 can be labeled as the hn, which is perpendicular to this dl, normal component. So the angle between normal component and dl is 90 degree. So cos 90 degree goes to 0. So these two components do not have any interactions with each other. So the only component of the magnetic field H that is available along the path dl is ht, because the angle between them is 0 degree. They are parallel to each other. So cos 0, 1. So h and dl are multiplied. So that means in this case, ht and dl are multiplied. So that means dot dl should be mathematically interpreted hereafter as tangential component of the vector field H. So the left-hand side of the equation is the integral of, it is not the integral of H, it is the integral of only tangential component of the vector field H over a closed path. Similarly, if you just work out for this particular path, and this is taken as dl, and this is parallel to this component, then this becomes tangential component for this side, and this becomes normal component for this side. This becomes 0 over this path, and this exists. So like this, we can find the product of tangential component of magnetic field and differential path dl for the complete closed path, and we can add all of them to get the closed path integration. That means the left-hand side of the Stokes theorem can be mathematically interpreted as integral of tangential component of a vector field H over a closed path. But physically, really, this tells something else. That is, integration, we know that it talks about the summation or the total value of a particular quantity. So in this case, the quantity is H, the magnetic field. So integration is the total magnetic field. So what is the total magnetic field? Which is aligned or acting along with a closed path. So the total magnetic field which is aligned with a closed path can be evaluated using the equation on the left-hand side. And this equation is also called circulation. Circulation. So that is integral of any vector field over a closed path is called circulation. So the circulation of a vector field, say H over a closed path, is given by the right-hand side. Let us analyze what the right-hand side is. In the right-hand side, the del cross H is the curl H. And curl H is always defined at only one point. And at the same point, there is some differential surface taken, ds. We know that S is the surface area present within the closed surface. That is, this is the surface area present within the closed path. So in this surface area, we have to start with a small differential area ds, whose direction is always perpendicular to its surface plane. So that is the ds vector. If you take the curl H is a circulation or revolution or rotation of a vector field around a point which is defined by ds. So here, if you call or if you define a curl at this ds, then this is given by del cross H. So del cross H is the circulation at a particular point, or it is the curl H at a particular point. So del cross H, because of this cross product, is always having the direction perpendicular to its own revolution plane or circulation plane. So that is also perpendicular to the surface of ds. So now the angle between the curl vector and ds vector is 0 now. So that means the curl H is also a vector similar to H. Curl H is also a vector similar to H, which can also be split into two perpendicular components. So one is curl H tangential component, another one is curl H normal component. Among these two, the normal component is producing the theta 0, so that cos 0 becomes 1, and this component exists. So that means the dot ds is mathematically interpreted as normal component of the curl H, whereas dot dl was interpreted as tangential component of the curl H. So at every point there is a rotational vector field, so that is defined by curl H, and all these curls available at every point on the surface within the closed path must be added. That is the integral must be added, and whose value will be equal to the line integral of tangential component of H over the closed path. So in summary, this Stokes theorem can be physically explained as any vector component can be evaluated over a closed path, let us say C. The same value can also be obtained by adding the circulations at every point on the surface to get the same value. So H can be either evaluated over the boundary line of the surface to get the magnetic field aligned with this boundary. Otherwise, the same value can also be obtained by adding all the curl normal components or all the curls of the same vector field at every point on the surface within the closed path. This is what the physical interpretation of the Stokes theorem. Now, I would like to give you the two statements formally. The statement of the Stokes theorem, the integral of tangential component of tangential component of dot dl of vector field, let us say H, any vector field H, over a closed path is equal to the integral of, again the integral of normal component is dot ds of curl of the vector field, that means del cross H over the surface S. So it is a surface integral S enclosed by the path C. So this is the Stokes theorem. This is how to write Stokes theorem from the statement, and we can understand both of them together. So the physical interpretation or physical significance of the Stokes theorem is that the total vector field aligned along a closed path is equal to the sum of the curl of vector field at each point on the surface enclosed by the path. Right? So after understanding the Stokes theorem, we can prove the Stokes theorem with few steps here. So to prove this Stokes theorem, we need two things. One is a surface, open surface, say S, that is enclosed by a path C. So we have to consider a surface, say S, enclosed by a path, let us say C. That is very important. We should define first surface and then corresponding closed path. But to begin with, I'm going to consider an incremental surface area or a differential surface area that is enclosed by another small closed path. Then later we shall integrate to get the total value. Okay. So now we shall also consider an incremental surface. Why incremental surface is required? Because we have to introduce curl of the vector field. So curl is defined with respect to a point. So that's why we start with incremental surface of area delta S on the surface S. We have the surface S already. On that we shall choose delta S. Let delta S be enclosed by the path Let us label the path as C1. C1 is the smaller closed path of delta S, or you can also say delta S1. Let us label it delta S1, the path is C1. So now I would like to introduce the definition of curl here for this particular incremental surface area. The curl H is defined by, so we should start with curl. So as per our previous discussions in videos, we can get this equation, curl H, normal component. The normal component of the curl H is defined by the limit, the incremental surface delta S tending to 0 over the closed path integration of the H, that is called circulation of the H, divided by delta S. Delta S is the incremental area and delta S is enclosed by C1. So that's why the closed path is C1. So this part, that is closed path integration over C1, is called circulation. Delta S is the area. Circulation per area is circulation density. As the area shrinks to 0, we get the definition of the curl. That is a normal component of the curl. Mathematically, curl H is given by del cross H. So this is derived using Ampere's law, is equal to the limit delta S tends to 0. So line integral of H divided by delta S. So after having this one, we shall introduce or we shall explain this N. N stands for the normal component of the curl H. So N gives, N represents right hand normal component. Right hand normal component of right hand normal component of curl H. So what is the meaning of normal? Right hand normal component. That means if you use your right hand so that the first 4 fingers are folded in the direction of the closed path, then the thumb represents the direction of the curl H. So that means if the thumb is indicated, so the fingers are folded like this, the hand, okay, please bear with the neatness of the diagram, and this is the thumb. Thumb indicates the direction of the curl H, whereas these folded fingers indicate the direction of the closed path. So this right hand thumb rule gives the direction of the normal component. Okay. So now the component of any vector can be obtained mathematically by performing dot product of that vector with unit vector in the desired direction. So you want to know what is the component of curl H in normal direction, perpendicular direction. So we have to perform dot product with A cap n. So that gives the required normal component. Delta S tends to 0. C1. The circulation over C1 divided by delta S. So now, to remove this limit, delta S tends to 0 from this equation, I would like to apply the limit to the right-hand side. Then upon application of the limit, delta S becomes ds, the differential area. So then the closed path is written as dl. Here it's going to be a very small closed path divided by delta S becomes ds. We shall still keep this C1. This further shrinks to smaller value just for the mathematical interpretation. Now, taking this line integral to the left side, we get curl H dot A cap N into ds. So in this case, this ds is not a vector. We know that it is simply the area. It's not a vector, it's area. Right. So now, A cap N being the unit vector perpendicular to ds can give us a simple representation ds vector. So every surface vector has direction oriented perpendicular to its plane, that is A cap N. So that can be combined with each other. So this is the simple form of Stoke's theorem applicable to a very small closed path C1. Very small closed path C1. But we want the theorem to be emphasized for the entire closed path. So now I would like to choose one more incremental area. Let us say this one, right? Let it be having some area, let us say delta S2, and this is also having the closed path oriented in the same direction of the previous. Let me call this C2, right? So now there are two curls here, one over C1, another one C2. So the total, by adding these two, we can get the total curl of these two surfaces. And if we observe carefully here, see the arrow mark, one is upward, another one is downward. So that way the common branch shared by both the surfaces will not have any field components. The field components gets cancelled out. So therefore, after adding the fields of these two surfaces, curls of these two surfaces, they are defined only for the closed path, which forms the boundary of these two surfaces. Boundary of these two surfaces, right? So likewise, if we keep on extending, if we keep on adding the incremental surfaces to this summation, finally, we end up with the closed path as the total boundary of this complete surface. So that's why C. So that means after adding all curls, so this fellow, the right-hand side is only for one ds we calculated. So after integration, addition is performed through integration. So if we integrate on the right side to add all the curls over the surface S, Then the left-hand side, the integral of h over the boundary called C will equate to the right side. So we can end the session by stating few comments here. In the same way, we can find equations applicable to all incremental surfaces of surface S. You can write equations for all of them. Therefore, the total vector field to be evaluated over the boundary. Boundary is also closed path, that is called C, is given by. So if you want to evaluate any vector field over the complete closed path, say boundary, then we can write that equation as closed path integration of H, that is equal to, we have to add all the curls of incremental surfaces, that is represented as integration here, that is curl H dot ds. So this forms the complete Stoke's theorem. In short, it says that any vector field can be evaluated either over the boundary or through addition of the curls of the field at every point on the surface. So that's about Stoke's theorem. Thank you.